Make sure the level comes down. The second hour has started. My voice is going to break down already from all the shouting, so bear with me. Thanks. Okay. Still on data and how to combine data. Because sometimes if you think about a question, let's say human depression, so a lot of data is being measured, brain images have been made, there's a whole world out there to think about it, psychological data, patient forms, you name it, there is a hell of a lot. And then somebody says, hold on a moment, would depression in people may be connected to weather conditions? And so, no, it's a good idea, there is some evidence to suggest that that's indeed the case. Ah, great, let's include the weather data. And then you're in trouble, for the remainder of days, right? Because there is no system to do this. So people have been thinking about this, and semantic web in computer science, so it's about meaning of data, not just numbers, but what does it mean? And you see in the search engine, if you search in Google, there is some kind of intelligence, but really if you use a word, Google can match it to that same word. But it's not so much dealing with the meaning of that word, right? So you could find related sites. My colleague, Frank van Harmelen, if you Google his name, in the Netherlands you just get to the village far more than to this man, although he's doing very well in science, right? Because, it's just that sort of searching, even with all the intelligence. So, steps need to be taken there. But some steps have been taken. Here you see a graph, and each of those points here in this graph, in this network, is a complete database. And so that's very nice, and I'll zoom in. Here is the life science corner. These in those days, slides a bit older, was the bio corner, say. So lots of connected data. And it was considerable work to make this linked data infrastructure to connect these databases. A lot of special one-to-one connection, and a lot of people working very hard to get this done, to extract some kind of meaning. So that has led to some interesting theories about information. What is information? And if you ask a computer scientist, what is information? Is there a unit of information? Ah, you bet. That's called a triple. A subject, you see it over there in the middle, a predicate, an arrow, and an object. So something saying something about something else. And then you see some examples, John, teacher of James, or something, or son of, or protein A, protein B, interaction. So you can put in knowledge like this. So fundamental unit has been argued of knowledge. What kind of knowledge? This is qualitative knowledge more than maybe the number knowledge, right? But anyway, this is what's happening, and you can build a whole information world using this formalism. And this has led to all kinds of other things. Nice. It's okay to be late, but if you call it talking, then that's not what we should have, and I'm already giving a lecture. That has led to the idea, what is an ontology, a structured vocabulary. The problem is, and I've already alluded to that biologists like to give different names to the same thing. And people, they might know, this word proteinase is really the same as protease. We know it. The computers won't know, you have to tell. So that leads to really structured vocabularies, and that has led in turn to the concept of ontologies. I think you've met ontologies already. Important database, do you remember which one? The Go database, right? There it is. Basically, most of the time there's a tree-like structure to lay down an ontology. But anyway, the ideas are you identify key concepts. What is important that the computer should be able to reason about with people or among themselves even. So we need to identify a good vocabulary. If it's mnemonic, if people like the vocabulary, that's good, but it should be a consistent vocabulary to identify all kinds of relations between concepts. That's of course what knowledge is about. And then they should be precise enough, not only to make people talk about it, protease and a proteinase, yeah, we know what it is. That's not good enough. Make it understandable between humans and machines, and even more importantly these days, because of scalability issues, computers should understand computers. Machines should be able to converse with machines. And this is the professor here I already mentioned. Because, you look him up, you go to a village more than his personality. So basically, RDF, this resource description framework, is a nice framework to put all this stuff in. So that has been used a lot. RDF is used a lot. There are query systems for RDF that you can look into the data and so on. That is really structured in a computer like this. And so that is nice. So ontologies normally are a tree-like structure. And then what you get is you have multiple data sets. And each of those data sets might have one or more ontologies, well structured, but then it's still a mess, a jungle of ontologies. So what do we need to be able to do? We should be able to compare ontologies and see, okay, can we find some stuff in this database that overlaps with stuff in that database? And then you need to sort of map the ontologies. So you can do that. And of course you can do all kinds of tree comparison techniques and find out, hey, this subtree in the ontology is really identical or very similar to another subtree. That's nice. So you get a shared vocabulary. But another thing is that you find out, a lot of data in these databases overlaps between these two ontologies. Hey, that makes it also important to look more into, to scrutinize that. And another thing is, of course, that you know all the stuff, background knowledge that makes you, these ontologies are really related. We should work that out. So that is all happening. So this is semantic web. It was a big promise. People really thought at the beginning that semantic web would solve all the meaning problems in the world. Of course, it didn't. Just like the genomics problem in 2000, everybody thought. And a lot of bioinformaticians started even promising that, now we have the DNA and we know cancer is a DNA disease, so now in 1 or 2 years, cancer will be solved, right? Of course, and these bioinformaticians said, yes, give us more money, we'll do it. That's, it's good to ask for money, but what you promise with the money, that's very critical. Because if you overpromise, you need to do some kind of expectation management. If you overpromise, you get in the valley of deception and disappointment, and that costs you dearly. When politicians get angry and disappointed, then that's not good. So, all kind of life lessons here. So, a little bit back to data problems. So, storage accessibility, that's all what we need. Data should be accessible. A lot of data is not accessible. You have to know where the database is. Maybe with some intricate Google search on page 14, you'll find some link if you're lucky. Is that good enough? Maybe not. Good public resources at least should be accessible. And so there are lots of issues there with data. Annotation of data, of course. What does the data mean? How was it measured? In what conditions? And so on. So an important phrase, and I'll get back to that, is metadata. That is data describing the data resource. Data about the data resource. This is a measurement for this type of cancer. This cohort of patients, it was done in that year, measurement technique was that, and so on. All of that stuff that makes people be able to use the data, okay, and know the data, and then you zoom into the data points themselves. So that's metadata. Sometimes people say the distinction between metadata and the data sometimes is not really clear. Metadata is data about. So, and all of this has become so big that universities start acting. Also this university, and they say, really, for all these data resources, so complicated. We can't, innocent scientists don't know how to store the data anymore. How do you do this with metadata? So we really need people to help them. And that is happening now. We get data stewards, and that leads to a whole new type of job in universities. And at the moment, you know how scientists are rated mostly? When you go to your dean, for your annual appraisal talk, what did you do? And so, publishing, right? Not only publishing, being cited. The H-index. How do people cite your work? And that is incredible. Yeah? And if you do it, but I'll tell you one story about this citation and the crazy counting world that we're in now. Everybody's being counted and tested, and your number, please, your H-index. Oh, only 35. Ooh, he's 36, so much better. We hired that person. Yeah, but I have all kinds of other qualifications. Sorry. No, it's the numbers that matter, right? So, here is a story for you. Papers that are cited 50 times is already good. If all the articles are written that cite your paper 50 times, and that's counted by Google, and that's all taken into account about your H-index, the more the better, of course. So a paper sounded 100 times is already nice, 1,000 is very many, 10,000 is huge, but tens of thousands becomes astronomical. So, one of my friends, Des Higgins, he comes back in the next course, ASA, a promise on multiple alignment. He wrote one of the early alignment papers. That paper got, in the meantime, cited 70,000 times. Well, that's more than most scientists or a block of scientists have in their whole of their career, a single paper. So that's nice for universities when they have that paper, right? So what happened? That paper was written in 1994, a while ago. In 2014, the rector of the chair of the board stormed into his office. You know, what did you do? Professor Higgins, you've ruined us. What happened? You know, in the world rankings, we dropped 50 places, and people tell us it's because of you. How can that be? How can that be? So let me look what happened. And so then they found out that paper. What happens in these world rankings, Wuhan, and there is the Times ranking, and we even have in the Netherlands the Leiden ranking, they're competing, you know, all these rankings things, they're the best, of course, and it's a jungle even at that level, but anyway. So the window, most of these counting systems takes 20 years. The paper was published in 1994. It dropped out of the scheme by 2014, taking a single paper, taking the whole university down 50 places on the world ranking. With ranking. So that means on one evening it's a great university, and the next day it's a useless university, right? That's the world, right? That's clear. We can count. It's true. This paper dropped out after 20 years. Why didn't we use 21 years? Then at least this university would have been great for one more year. Sorry, it's 20. Be happy it's not 19, right? So you know, this is the logic we work with, and we think it's extremely important. So anyway. Sometimes counting is good, but not always. That's the message here. Okay, quickly on about data. So you can data use in a wise way and in other ways. Okay, so what is all happening? You know, if you have data and it's important, your experiment should be well described. It should be a good experiment, of course, but it should also be well described. So experimental design, your data design. When you store data, why would you do that? Is that just for use yourself to look back after a month? Or should you store it in a way to allow other people to use your data? That is more interesting. So if you take that decision, yes, my data should become available to others, then you have to think about you know, how to publish it in a way that other people are able to understand what is happening. So you talk about storage and networking, of course, to get your data stable. Should it be on a laptop only, or should it be well connected to the internet? And should you fill the form that your data will persist for at least 10 years? Sustainability of your data, all of that is happening, and important resources should be treated well. You know, you will work with databases, Swissprot or Uniprot. If that database is switched off, after 2 days the world will turn more slowly, right? Because this is a very, very important resource that daily science needs. So, should we just be careless about that? No, maybe not. Not too long ago, I'm old enough to know that this database fell off the planet almost. Thank God Swissprot, and we had to all sign a scientist. The Europeans were in deadlock because the Swiss had made a rule like if Europe gives money, we don't, and Europe in the meantime had made the rule that the Swiss give money, then we don't. So, you know, you add it up and nobody gave money. And so then the Americans came to the rescue, as often happens. They paid for a year of this database, and then, you know, Europe had the act again together, and this that was science. So there's a lot of politics as well, right, behind all this. A lot of important stuff. Okay, so I'm going to talk about some more recent developments. Not only, you know, this is all important, and now you might have heard of this term, be honest. Who has heard about this? Fair data. Fingers, please. Okay. So honest, so 3, 4, 4.5 students, roughly. One finger at a fleet. So what is fair data? And this we talk about. So this is about, you know, using other people's data principally. So it's an acronym. It stands for findable. A good data resource, that's important, should be findable. That's first off, right? If you don't know it's there, you can't, then that's the end of it. But if you know, if you locate it, we talk about persistent identifiers and all kinds of technical stuff here. You know, that the physical location, if they change, it should not, you know, make that at once the data is not there where it was. It should be addressed in a way that you still can go to it, it's well identified. Then if you have it, it's accessible. So the data, you can get to the data, it's reachable over the internet, hopefully, and then you can maybe get into it. But accessible doesn't mean you will access it, it's accessible. Sometimes medical data sources, without ethical consideration, people say, you don't put this data out in the open. The idea is the metadata about the resource is out in the open, so you know it's there and what is in it. But if you go, you need to go to an access committee, you need to show that you're a medical research, so there are all kinds of things, and that's maybe for good reasons. So accessible doesn't mean that you will always get access to it, but it should be regulated how you can get access, and that should be open as well. So that's accessibility, then the I is already there, maybe the most important matter, interoperable. We're all talking about combining the knowledge or extracting knowledge from a combined set of data resources. That's very important. With all the things you need there in place, I'll talk a bit more on that in a moment to make that happen. And of course then, the end result will be, if you do all of this, the data will be reusable for other people. And you know what? Maybe sometimes for another purpose. I'll give you a Siemens example from this country. Suppose there is a database of some church history scientist, scholar I should say, church. He has taken all kinds of pictures of Dutch churches from whenever they started over the centuries. Nice database, it's findable and so on, and it's all there, well done. And then in one of the villages where there is a church, a murder was committed a couple of years ago, and the detectives tried to get their hand, but they can't find the murderer. And there is one person who was suspect. He was called in and he said, no, I wasn't there that day. Asked my wife, asked my nephew. They can't get the finger, they know. And then he's standing in front of that church, brightly smiling on that day he said he was in the village. In the church database. That database has not been compiled with finding criminals in mind, but if you do it, you know, the data can be used for another purpose. So really reusability is the data, the resource can be reused by others, maybe for a different or new purpose. That's very important, and that is really something, if you can do that, and that's not easy. Normally what happens if you made a data set, you wait 2 months. You will not know your own data set anymore. Really, you think, oh, I'll remember this, you know, I've done this so many times in my life. This code, I don't need to put comments in my lines. I remember it. You look after a year and you think somebody else wrote this code. I have no clue what's happening. So, you have to be better there. There is help now. There's GitHub and doing that. Okay, so that's all important. So this paper, the FAIR principles were discussed in a Lawrence meeting in Leiden in 2014. This paper was written, many people and the authors, I'm one of them. So this FAIR word, some of you heard it, but now in politics it's big. The EU only talks about it. The G7, the G20, it's all data should be fair. So this has been flying. And now we try and approach the Dutch government and tell them, look, you know, we made this happen. You know, the whole world knows about FAIR. It's a great success, you know. There is a move. And now give us some money to do something. The Germans give money. The French give money. You don't. We'll think about it, guys. Don't call us. We'll call you. That's so far the reaction here, which is a pity. It might be overtaken by other countries. But okay, on a world scale it happens. Only these few Dutch guys are angry. Look, okay, me. So, a bit more detail, and then I go to the, why is this hanging? Yeah, something is happening. Okay, so I'll go through it because it's always annoying. Okay, so here you see about the 4 words: findable, accessible, interoperable, and finally reusable. So this is the worked out FAIR principles, right? You see metadata coming up a lot. You know, some data resources like imaging data, it's difficult to get really the data points fair. What do they mean? Each data point, you know it only as a picture. If you look at it from a wider perspective, but at least the metadata should be fair. So fair data, the data should be fair. Even a verb now, verification of the data, verification software, it's all flying at the moment. But these are really important principles and considerations, and the idea is that public databases produced by public money should be fair. And that's not, you need to do things. Think about the data. You need a data management plan, you need data stewardship, you need long-term total preservation. All of that has to be arranged. Which scientists normally don't like, because they don't want bounds, they don't want, you know, frameworks within you have to operate. They want total freedom, right? But then again, you know, think about it. If your stuff has to be useful. We put ourselves, you know, we write papers, we put a reference list and exactly, you know, and there we say, is that freedom? No, of course not. But, you know, so it's a matter of getting used to it. Okay, so a few things that are needed to do data stewardship in this kind of going to fair data. You need a data management plan. What metadata, what ontologies. The best would of course be if you have a community embraced ontology. An ontology where people in the field say, yeah, I like that. The terms are good. I think we can work. Or they all say, I hate it. Then you know one thing, your data resource won't need it. So you need the management and very importantly, of course, for the important resources, long-term preservation. And you know, science, how that goes, at best, in 4-year cycles, like politics. Money flows for a few years. So how do you promise that the resource is there for at least 10 years for people? Very difficult, right? So, and normally what even happens, you know, you write a grant, you send it to NWO here in the Netherlands, you say, we have a totally new database, it will change the world, fantastic. They say, oh, this sounds beautiful, you know. Take the money, make that thing. So 4 years you work hard in your team, you have this great database. It works, the world thinks it's important, so after 4 years you go back again and you write to NWO again. You know, it's a great success, the database. Give us money to develop it further. Ah, where's the innovation? This is not new. Rejection, right? That's normally what happens. So you're a victim of your own success, and if you have no success, you know, that's the end of it anyway. So, difficult, long-term preservation is really an issue. Okay, now there are lots of positive things. So this is basically what you need as a minimum. You know, you need a resource, you need good metadata, and for accessibility you need a license. Who can access the data under what conditions? So these are prime things that should be. So basically what we're trying to say is fair data is like an hourglass. The conventions we need to make are really here, and we compare this very often with the internet as we know it. Lots of protocols, you use stuff you don't even know, HTML, XML, you know, for knowledge extraction, and so on. But what is here? Why is it such a success? There's one little protocol, in a few lines, TCP/IP, to identify nodes in the network. That's really carrying the whole lot of what we're doing. So the fair data principle should also be, I mean, really only the very principle. So that's what we're trying to do. So what do you normally have? And this is just an easy sort of example. What can help? Here is a question. I need to combine what is it, Alzheimer's disease and Huntington disease data to devastating neurological diseases. And here are the database owners. They say, yeah, we're very helpful people. Well, of course, you'll get our data. That's a good start. So there we go. The data comes forward, and one is in, I guess, Chinese or something. Who knows? Ideograms at least, and the other is like Russian. So different data, difficult to combine this. These sets cannot talk really, right? That's a problem. So what do we need to do? We need to solve this problem. We need to make data formats interconvertible. That you sort of get this idea, that you really get the concept of interoperable data. So that is the state of the art. And then there are players in the field. Perspectives, you could say. You have data producers making the data resources. They need to think about users, of course. And there are normally users who only think about themselves. And there is sort of stuff in the middle, you know, that's produced and used. And so the data producer might say, yeah, stewardship, sustainability, long-term preservation, privacy. Ooh, I don't want to give my data away. A lot of people, they think, you know what, I put all the trouble into making this data. I want to get the time to think about it myself. I won't send it out in the open. Then all the clever people write the articles. I need some time. So there are all kinds of psychological things that you know, inhibit people, prevent people from really opening up easily. But nowadays, that's we're mandated to do that. It's an obligation. So licenses, access, maintenance, storage, all that. So what is the computer? So in the middle is all kinds of stuff that's made. So here you see the word Excel. You know, even that should be there. A lot of people sitting in the medical arena, horrible. They use Excel. Doesn't scale. Anyway, You need to deal with what people do. And then there are all kinds of formats. And TICOM is a medical format. Sparkle is the querying system for RDF. It's the system with the trees and the triples and so on. That's good to know. And then, there is the user, and he thinks, how can I get to the data? How can I find the data? Oh, bloody a license. How can I get a license? So just the things to get the data and be able to analyze the data. Maybe publish beautiful papers. So what kind of architecture, data architecture are we thinking about? So here is raw data, all kinds of data generation. Big flight is a stage in the last decades, right? We can measure more than ever before. So basically, the bioinformatician comes into play when you say, data is in some kind of file. I want to read out numbers or something, statements, something that I can read to the computer. Then the world starts. So it's next level, you can need to convert that. Then there is another level. This is sort of the fair level, where already this data and the different data sets are linked up in an interoperable. That will be very nice. So when you have that interoperable world, in whatever way, it can be done in different ways. But as long as it's really interoperable, you can go to the next layer and really do the integrative analysis, right? Analysis, and that should all be high performance. So this is sort of the ideal world, and that means that we get data points, open access points to the internet, call those oops, press one more button. Data fair ports, they're called. See the button. And so basically, just like airports, you see all kinds of larger data centers that open up their data in this fair way so that people can use it. So it's distributed data that can be really used as one resource. In the old days, people will always talk about a data warehouse, but what you do, you would download all these data resources, stick it on your own disk, and then worry about it, then you're full control. Well, that sort of approach doesn't scale anymore. There's too much data just to download. Give you an example. There is an important bioinformatics lab close to Cambridge in the UK. It's called EBI, European Bioinformatics Institute. Go there if you have a chance. Great institution. Next to the Zanger Center, another great institution. Then there is the NCBI, close to Washington in the United States. National Library there. And they said, you know what? We do each other's backup, daily backups. We do it physical. We send each other the data over the internet daily. And then, that's great, and we can do that for one another. And then it turned out, oops, the sheer size of the data made that it would take 3 weeks over the internet and not arrive. There would be a fault. So, too much data. So what happens? They paid students. They said, would you like to go to Washington, stay the night there? You just have to deliver a big disk, that's all. Daily flights back and forth. That's modern times, right? Top of technology. The internet, forget it when you talk about that. Really, steps have to be taken. So they stopped doing that. They have another solution now. In the meantime, this has happened for a couple of years. The students liked it. Quickly into Washington. Easy, 8-5 days. That was all paid for. Very nice. Okay. So basically, what kind of world do we want? There is the data, and then there are the tools. And I told you this example of, we used the wrong tool for the data. That's not a good idea. And then, on what computational resource do you run it? On what cloud do you run it? And then it could well be that you have a big system, everything is perfect, all the data is pooled, and made interoperable, and you ask an intelligent, integrative question. And then you want to run it on the Amazon cloud. And then one of the data resources says there was a little statement in the metadata. Oh, this is privacy reasons, not on the Amazon cloud. Oops, okay. The system should be intelligent enough to sort all of this out. And that is really, then if you can really integrate these steps, the physical world, the compute world, with the data and the tooling, the analytics layer, then we're really in business. And what can we do then? Maybe overhead-free, no data wrangling anymore, no years of trying to pull data and sort out the terminology. It's all there. That would be beautiful. Right? You can do science, not all the preparatory. So, and if you have that, this is the slide I showed you before, based on this technology, there is some software now. So this is now a knowledge graph, it's a big network, but it's extracted from all of the pooled data. And this is, for example, the knowledge graph about a bug. No, malaria, let's say malaria. This is the disease malaria, what we know about it, the proteins, whatever is there to be known. And this is what we know, the knowledge about a bug. And then some smart guys asked the question, would malaria have something to do with the bug? You know the answer, right? So then you enter that question, and you see then that this is really on the screen, it happens. You see these two knowledge graphs move to one another. It's time to sort, and you see just the overlapping, qualitatively the overlapping terms. Hey, this protein is in this bug, and it's somehow important for malaria. Hey. So I did these tests, and this is just based on concept like transitivity. And it's basically a very simple concept. If A is linked to B, and B is linked to C, then A is linked to C via B, right? So you can go from A to C, the pathway is there, and you do this, and all sorts, you get something like that. And there is more to reason, but only based on transitivity, you can already surprise medical doctors who react like, ooh, you know, I knew about this protein, but these other 15 proteins I've never known. I'm 20 years in the business. So there is a lot of data out there that cannot be met by the human eye. You know, it's sheer size and scalability of it. So these are really important techniques that lead to very important questions. So that's hopefully part of the future. Okay, I'm a little bit drawing to a close. I hope I can show you the movie, but video doesn't seem to work, so I need to come close at the end of this lecture and do it on the sound of this laptop. Let's see what happens. Okay, so what is there in the Netherlands? Just to give you in all of this. So there are many training efforts on data interoperability, on data stewardship, many courses in, I'll flash them by you in a moment. DTL, Dutch Tech Center for Life Sciences in Utrecht is a national platform, important one. There is the Research School for Bioinformatics and Systems Biology. They have a very nice workshop, conference, two-day conference in London every year. Try and go there. It's really nice. There's a pub quiz in the evening, good food, and nice science talks. A lot of fun. Early run in the morning for those who want to running. And then there's every year. There's a European project, Data for the Life Sciences, and there is a Dutch node, which separated divided over Europe. And we have Elixir Netherlands. So I'm going to show a few things about it. So, it's not about the details. There's a whole data program. You can go on the DTL side. So there's a lot of software, carpentry. You know, you do a Python course here, but there is of course more stuff to be done if you want. So there's really a lot. Galaxy training, important biological query system is there, so you can do many things. And these courses can be offered by DTL or Elixir, as you can see here. This is just a course offering, the national course offering. Here is Elixir, it's a European network. It's an S3 landmark, it's called. S3 is European Research Infrastructure. It's a very successful project, this one. And the Netherlands has a show of joins. Just screen saved bit on their website, so there's really something there. And this is maybe good for you to know. There is the TESS, which is the Elixir training system. Huge numbers of courses and stuff that is happening in training land is there. So it's good to, if you want to think findability of training resources, try this. Because the data problem is also for the courses. There is also findability, accessibility, interoperability, and so on. So fair data query everywhere. Here you have the BioB School, the Netherlands Bioinformatics and System Biology Research School. See how your master program is called? You see, you don't need orthology, right? You see that? There is a reason behind all this. You can imagine. We were there at the start of this thing. It's hard, right? So they do lots of things. I said already, there are good courses, PhD level courses, but there's a master student you can join if you're interested. And you can go, so this is basically meant for PhD students, but master students are becoming more and more important. There's the Young Student Club, Student Committee, the Regional Student Group, or the Young Computational Biologists. Master students can be active there as well. Let me tell you, if you do that, you learn more than in this master program in a sense, right? You start learning and talking and organizing. That's very good. Even more than in this master program, mostly. Okay, so there is DTL, the Dutch Tech Center for the Life Sciences, standing for Data, Technologies and Learning, and also the Dutch Tech Center, so it's a double acronym you could say, and multiple coding, happens also in biological systems, by the way, DNA level even, gene in one direction and the other strand another gene, or even in some viruses, this bit of DNA is used for one gene and a bit another one, because you have to be economical about structure coding, really interesting. What happens in evolution when you have that? But lots of stuff, lots of courses and so on at the end. Yeah? This sort of now, what can we all do? I'll give you a few examples of big data and big computing. Here is one. I like this one. This is about HIV, and you know HIV is a virus, right? And that leads to AIDS if you're unlucky. And so what did people do here? There are a lot of drugs on the market, and they do stuff and they can be repurposed. So the idea was, what kind of existing drugs in a cocktail could we give to those patients? That was in the days when these cocktails were not so very successful. So what happened? They used all of those pharma databases with all of the chemical substances. So had a drug database combined. And then they started mining, or, measuring all the genomes, do all the sequencing, get the patients, then try and recognize the viral part. The virus is a sneaky thing, right? It enters itself into your DNA. So try and find the viral, try and find the viral sequence that encodes the protease, because the protease was an Achilles heel of the of AIDS to solve it. So then they had those, and then they started just modeling the protein structure. There will be a course, structure bioinformatics. After that course, you know all about that. Now it doesn't matter. So they built a three-dimensional structure, because then you can dock, you can really do a computer experiment to see which protein binds well to what drug, what inhibitor. They did all of this so you calculate yourself silly, get lots of data over the line and so on. But then in the end, they could prioritize the drugs, repurposing this drug and in combination. So, and this even worked pretty well in some patients. So there you see that big computing, tying together data, integrating all of stuff, do a lot of computation, do your modeling, and then all of that in combination brings you somewhere. Okay? And these were difficult steps. So this is done for cancer now as well, these techniques, but cancer, of course, are so-called complex diseases, multi-gene diseases. There are a lot of simple diseases, I can tell you. For example, this one, DMD, Duchenne is a muscle disease. Its voice gets deformed and you die pretty early on. And it's just a single gene. It's the biggest gene that we have, roughly 2.5 million base pairs, bases, and a couple of genes on it. And then there is a mutation, you've heard about that in the last course. And two kinds of mutations, a frame shift mutation, does that ring a bell to you by now? Good. And a non-frame shift mutation, which leads to different severities of the disease. What is now the technique? So they've tried to do gene therapy. These single gene diseases are great candidates for repair, on the gene level. Put a proper gene in and hope for the best. And that was politically difficult because, patients would die, have died over the years in early steps in these type of approaches, and so that was a problem. But now there is CRISPR-Cas9. Heard about this, or basically you might say this is technology that allows you to stick a gene anywhere in the genome. It's bacterial origin, that's where the names come from. So there are a couple of drugs. I can tell you hair-raising stories about drug testing and how this one miserably failed the test because they had said good patients can walk for 40 meters, and as a measure of success. They didn't get there, they got 39.6 meters, right? And then they say, that's a failure. They say, these boys are doing so much better, The parents are elated, it's fantastic. No, you failed the test, no further money. It's that counting, right? So that's being repaired. A lot of frustration, but years later. Okay, so this is sort of a simple disease, but it doesn't lead to simplicity if you need to treat it. I do know about it. CF, cystic fibrosis. It's not very well known here, although there are certainly patients in the Netherlands. But in the UK, the incidence is a lot higher. In Ireland, it was called the Celtic disease for a while, and in America. It seems that Ashkenazi Jewish population have a higher incidence of the disease. It's a simple genetic disease with a little error on the genome. Very simple error, really. Here it is. A deletion of 3 base pairs. Although it's not perfectly in frame, as you can see there, ATC and TTT. It leads, if you miss those 3 red letters there, you just miss phenylalanine in the protein. The phenylalanine happens to be on the surface of that protein. interfering with the recognition of the protein in the cellular system. So this protein gets degraded far more than you would like to. It's a good guy that is now recognized by the system as a bad guy. That's a problem. Autoimmune, you might say, within the cell. And so this leads to that chlorine and so on cannot go through the cell. So it leads to dietary problems, and normally you die because of mucus in your lungs. That is also one of the results or one of the consequences of this disease. I did show it. In the meantime, we know, so it's very difficult. So we know the cause. We know it exactly. Repair the gene. Put the gene with these 3 letters in. Done. Very difficult. How to administer the drug. How to do this. Germline or somatic. What do you do? With inhalers in the lungs, they've tried it. Put a weakened virus in. Put the good gene on the virus tricks us. We trick the virus with a copy of proper gene. Then inhale the virus. It should not be AIDS as a virus. Then you die of another course. So it should be a weakened common cold virus or something. So very complex. You start pulling and, oh, then we have to put immuno. We get that this is, the body doesn't react well. We have to weaken the immune system. Oof, then you get all the trouble. So, yeah, it's a landmine field. And this is for simple diseases, single gene diseases. So, what do we get anyway? So this was showing you that life can still be complicated when you want to do things, but we need people who are still able and courageous enough to dive into all this. So, but in medicine a lot has happened, and the catchphrase is from bench to bedside, so we should need the genomics lab and we need to bring that into the clinic. Patients should really benefit from it. So that should be a cycle between researchers and biologists. Okay, so, and for cancer disease, what you normally get, and even for CF, there are a few dominant causes of a disease, but you always have the so-called long tail. Other genes are also there that also have an influence. They can lead to disease. In fact, a lot less frequently. So it's not that you, very often, even a simple disease, not a single solution. You need multiple solutions. That's a problem. So this was not the current president, but the last president. So we have here a bit of presidential history. This is not photoshopped. He really had a DNA molecule on his desk. Amazing man. He liked science. And he announced the Precision Medicine Initiative. And that is what's happening world over a lot. Personalized medicine and precision medicine is going to take the stage. And what is the simple, for example, simple application? You have patient groups. What's the beauty of sequencing? You can recognize people not on how they look. It's really on the genetical content. So you can group people like for like. Genetically you're like. So we think that what works for one person in a group might as well work for another. That's a different approach than aspirin. The whole world should eat it. And everybody happy. At least Bayer is happy, the pharmaceutical producer. So basically you have drugs that are normally toxic. Well, many of them. So what's the best drug? Not toxic and it works. What is the worst, of course, possibility? It is toxic and it doesn't work, like many chemotherapies. So that's a big problem. So what can we do? The like for like, based on genomics, it is very important to be able to cluster people and appreciate differences between people. That's important. And the idea is that what will happen is in the modern world that it's not only treatment, so we used to talk about medicine a lot, but now it's about health. We should try and prevent disease. So here is when a person is healthy. On top there in the red is disease, and there is the risk area, anesthesia. So basically, lifestyle, diet is really important in combination with drugs. Because even if you have a personalized drug, you go to Bayer or a big pharma company, you say, look, for this person, we have now found a personal drug, it's fantastic, no side effects, the guy's cured, terrible disease, beautiful. Could you make the drug, Bayer? And they say, oh, come on, there's the door. We want blockbuster drugs, low development cost, and everybody eating it. And n equals 1 medication, are you crazy? We don't play this game. So that's a bit of a problem. And so then you say, combination therapy, lifestyle in combination with diet makes for many possibilities. So maybe then you can treat people in a personal manner, and that is more and more. So prevention rather than treatment is now, and doctors need to get used to it because they say, hey, we are here to make people better if they have a disease, right? That are telling me. Should I eat oranges? Not interested. So, and even an orange, I say the word. My mother, and maybe even your mothers or fathers, told you, eat an orange, it's good for you. It turns out now, on genomics, that for some people oranges are good, but for others they're not, really. Oranges are not good for everyone. Vitamin C. So, we need to really think a little bit, and if this is done for oranges, there will be more food sources for the same one. So all this old knowledge is, of course, eat oranges, I would say. No, I didn't tell you not to eat oranges, okay? I still think it's a good idea. But as I said, not for everyone. So this is the future, I think. And now I'll try and play a little. I'll wrap up, and then I'll try and switch this on. Oh, it's already you can walk out, so who wants to stay here and listen to the movie? I'll put it on if it works, and then the others can go to the practical. So basically, big data, information sciences, complicated world, a lot of fun to do big things, to work out big ideas, and to make this infrastructure that will allow people to really ask intelligent questions about complex science. So, and of course, one of the big applications is personalized medicine, precision medicine. There's a lot of money there, so you will see that bioinformatics and systemology will, of course, pay a lot of attention to this application. Right? Plants are important too, but Asian societies, there's more money in the medical arena. So, with that, thank you for your attention. For those who want to do ASA, algorithms sequence analysis, that's next month. I'll do that course as well. And have fun in the day. I'll switch on this film.